Stefan, do you have a sec? I had a question about today's lecture.
Just 1 second. I'm about to have the high score in Grand Theft Auto. Yes! Sarah, come on in. I always have time for my Biology 125 prefect. Why, Sarah? What was your question from today's lecture?
I understood what you were saying about the synthesis being different on the two strands.
Mm-hmm.
But does that mean there's more than one DNA polymerase?
Oh, good question. Is there more than one DNA polymerase? Well, let me first ask you, which of these two strands is going to be replicated continuously? Now keep in mind we're dealing with a bidirectional replication. Forks are going in both directions. But I've drawn up here just the leftward fork. So we're moving from right to left. This is our direction of synthesis. Which of the two is being replicated continuously?
I think it would be the top one, because you're going, the new strand will be 5' to 3'.
Excellent, excellent. Correct. And you would first start with a short primer made of RNA in this case. That short primer would have a hydroxyl group. And then DNA polymerase would attach to that hydroxyl group. I just so happen to have a stand-in for DNA polymerase that's going to be replicating that top strand. So this DNA polymerase molecule starts attaching nucleotides from that free 3' OH, and here we go in the 5' to 3' direction, continuously. And let's just leave the first DNA polymerase at this spot right there. You're correct. There is a second DNA polymerase involved, and that's involved in replicating the discontinuous strand down here. We need primers again. A primer will bind right here, an RNA primer. That RNA primer is extended by the second DNA polymerase. And this DNA polymerase would extend in this direction. Now, of course, this DNA polymerase is then free to interact with the next Okazaki fragment, where another primer is laid down. And then another round of synthesis. So why don't we stop right here, and that's where our second DNA polymerase will be sent. So yes, there are two different DNA polymerases, one for the continuous strand replication, one for the discontinuous strand DNA replication. And Sarah, I wouldn't be surprised if you got another question in the prefect session. It namely has to do with the removal of this RNA primer and how this gap is synthesized. So after this second DNA polymerase has left, this piece of RNA will be removed. So let's remove this with that enzyme RNase we talked about in lecture. Yes, you have a little gap right here. At this point, another polymerase enters the picture, DNA polymerase 1. DNA polymerase 1. And it can attach to the free OH group that's at the end of this DNA molecule, and it will synthesize DNA so that gap is filled. And Sarah, we also have to remind the students that how is this final tiny little gap filled right here? What final enzyme are they going to need to make that covalent bond between the sugar and phosphate of these adjacent nucleotides?
I think we're going to need some DNA ligase.
DNA ligase. That'll be the last player in our little skit here. And that's responsible for making that covalent attachment. I wish I had another player, but they'll just have to take our words. DNA ligase. I think that should settle their questions quite nicely.
I think so too.